everyone, I am Nikita Murthy, Faculty of Information Science and Engineering, Maharaja Institute of Technology, Mysore. Today we are going to study a topic called Pipeline Reliable Data Transfer Protocols. Pipeline Reliable Data Transfer Protocol. If you remember, in the last session we were talking about RDT 3.0, RDT 3.0. In the RDT 3.0, it was supporting all kinds of scenarios where it was handling detecting the errors. If the packets while transmitting get corrupted, that was also it was getting detected, recovered also. If the packet get lost, that case also it was addressing. But this RDT 3.0 is a stop and wait protocol. This RDT 3.0 is a stop and wait protocol. What do you mean by stop and wait protocol? When the sender sends the packet, it will stop the system and it will wait for the acknowledgement to receive from the receiver. Only after receiving the positive acknowledgement for the sent packet, this will start working again. That means it will start sending the second packet. Now, in the today's high speed internet world, do you think this slow performing RDT 3.0 it can catch up the speed? No, right? It has few performance issues. To check the performance of a RDT 3.0, let us take an example. Consider two hosts. One is located in the east coast of the United States and the other one is located in the west coast of the United States. Let us try to analyze few things. Let us consider R be the transmission rate. Let R be the transition rate of a transmitting channel, and then with the packet size L, R be the transmission rate and L be the packet size. Let us consider packet size be 1000 bytes. Let us consider packet size L be 1000 bytes. That means 8000 bits. That means 8000 bits. The time needed to actually transmit the packet into the 1 Gbps link is as I could see in the formula, it is D transmission is equal to L by R. That means L by R means packet size divided by the transmission rate, that is 8000 bits divided by 10 to the power 9. R is, as we are transmitting into the 1 Gbps link, R will be 10 to the power 9 bits per second, which comes out to be 8 microseconds. Let us suppose if this is the sender and this is the receiver and this is the packet being sent, and this is the packet where data is residing. Here is the sender, here is the receiver, and the sender is sending the packet to the receiver. Now, suppose the packet is sent from the sender at t is equal to 0. If the packet is sent from the sender at t is equal to 0, then the receiver will receive the packet, the entire bits of the packet at t is equal to L by R. That is, as we saw in the formula, it is 8 microseconds, 8 microseconds. Now, since the two hosts are at a country apart, that means a sender is at the west coast of the United States and the receiver is at the east coast of the United States. That means their packet is traveling a cross country. Now, suppose it is traveling few minutes, then if the sender has sent the packet at t is equal to 0 seconds, the receiver will receive the entire bit, the last bit at t is equal to RTT, that is round trip time by 2 plus L by R, which comes out to be 15 microseconds. So, the last bit of the packet will arrive at the receiver at t is equal to RTT by 2 plus L by R. Now, after the receiver has received the packet, the receiver will send what? Acknowledgement. The receiver will send what? Acknowledgement. Let us hope the acknowledgement is very small packet. It will arrive soon. At what time it will arrive? T is equal to RTT plus L by R. RTT plus L by R, which comes out to be 30 microsecond, which comes out to be 30 microseconds. So, out of these 30 microseconds, that means from the sender, the packet being sent to the receiver, and then to receive the acknowledgement, for each packet the sender has to wait for how much time? 30 microseconds. Out of this 30 microseconds, the sender was utilizing only how much? 8. The sender was utilizing only 8 microseconds to send a packet, but the remaining time the sender was waiting to receive the acknowledgement, isn't it? That means sender, for each packet it will stop it and it will wait for the acknowledgement. Out of 30, only 8 microseconds it is utilizing. The utilization time of a sender is only 8 microseconds, and the remaining seconds is wasted in waiting. So, this is the major performance issue which we can found it in RDT 3.0. Now, let us look at the how much utilization of a sender has been done. The formula is so, the formula to know the utilization time of a sender is U sender is equal to L by R, RTT plus L by R is equal to, it comes out to be 27 microseconds. That means the sender was only utilizing 2.7 hundredth of 1% of the time. That means all the time it was simply waiting to receive the acknowledgement. As you could see in the diagram, that is what they have explained in the diagram. From the sender to the receiver, the first bit of a first packet is sent from t is equal to 0, and it has taken t is equal to L by R seconds to send, L by R time to send the entire packet, and then after receiving the last bit of the packet at the receiver side, the acknowledgement has been sent, and the acknowledgement has been received at what time? T is equal to RTT plus L plus R. After receiving the acknowledgement only, it is sending the second packet. The only solution to this stop and wait protocol is to, instead of sending only one packet at a time and then waiting to receive the acknowledgement, we can, if it is possible, or we can send a multiple packets. We can send a multiple packets from a sender to receiver without getting the acknowledgement for that. That means, instead of sending only one packet at a time, what we can do? We can send multiple packets to the receiver. After sending a few allowable or few finite number of packets to the receiver, we can then receive the acknowledgement for each of the packet that has been received. Then here, to make this possible, we need two approaches or two mechanisms. The one mechanism is to increase the sequence number. In the earlier session, we used to see the sequence number was only between 0 and 1. If that is the case, we cannot send multiple packets, isn't it? For that, we have to increase the sequence numbers. Not only that, we need to have a buffer. We need to have a buffer both at the sender side and at the receiver side, because whatever the multiple packets that has been sent by the sender, that has to be received by the receiver in a buffer, so that it can receive it in a order. Whatever the packets that has been sent, to receive it in order which they have sent, we need to have a buffer at the receiver, and the acknowledgements that has been sent by the receiver, it has to be received by the sender side buffer, so that it can know for which packet the acknowledgement has been received. Both of these approaches are available in a mechanism called pipelining. Both of these approaches, and the solution to the stop and wait protocol is to have a pipelining solution. This solution has two types. One is go back N, another one is selective repeat. So, pipelining has two methods, one is go back one, another one is selective repeat. In the diagram you can see the pipelining operation, pipelined operation here. From the sender to the receiver, the first bit of the first packet that is sent at t is equal to 0, and then at t is equal to L by R, the last bit of the first packet is sent. Immediately, without wasting time, the second packet is also sent and the third packet is also sent. At the receiver side, the first bit of the first packet is received, last bit of the first packet is received, last bit of the second packet is also received, last bit of the third packet is also received. As soon as they receive the packet, the acknowledgement has been sent, and then at the sender side, the acknowledgement arrives at what? T is equal to RTT plus L by R seconds. So, here you can see, instead of sending the one packet and then waiting for acknowledgement, here we are sending multiple packets where we are able to catch up with the performance speed. Now, let us look at the first method of the pipelining, that is, first one is go back N. Go back N. Here, go back when, as it is a pipelined operation, it will allow us to send a multiple packets. It will allow us to send a multiple packets without waiting for the acknowledgement. That means, it is able to send up to n. It is able to send up to n. It allows up to n finite number of packets to send from the sender to the receiver. That means, n is the maximum number of packets that could be sent from the sender to the receiver without waiting for the acknowledgement. Before we begin with the explanation, I want you to know a few basics of the go back N protocol. So, let us look at the basics. Here, these are the packets that has to be sent from the sender to the receiver. Here, this is this base points to the packet, this base points to the packet which was first sent to the receiver, but the acknowledgement has not been received. That means this is the oldest unacknowledged packet. That means this was in the sequence, this was sent first and we are waiting for the acknowledgement for this packet first, okay, and then this will be in the line, and then after receiving the acknowledgement for this, then only we should receive the acknowledgement for the next packet. That means this is the oldest unacknowledged packet. Next sequence number is pointing to the packet where this is the sequence number of the packet that has to be sent next, in the sequence. That means next sequence number is pointing to the packet where it shows the sequence number of the packet that has to be sent. The range 0 to base minus 1. The range 0 to base minus 1 will point to this here, these three, base minus 1, 0 to base minus 1 are those packets that has been sent from the sender and received by the receiver, and the acknowledgement for these packets has been received by the sender. Next sequence, base to next sequence number. The range base to next sequence number minus 1, that means these sequence. What does it say? It say these are the packets that has been sent from the sender, received by the receiver, but acknowledgement is not yet received. The acknowledgement is not yet received by the sender. Next range. The next range, next sequence number to base plus n minus 1. That means these are these sequence. That means these sequence. These are the packets that has to be sent next in the sequence, in the pipelining. These are the packets that has to be sent next to the receiver in the pipelining. The next range, base plus n. The next range, base plus n, that means it is greater than these sequence. The packets that are greater than these sequence, that means that are greater than the allowable finite number, those packets should not be sent immediately. Those packets should not be sent immediately as it is greater than the allowable number. So, here we should know a point. The packets that has been sent, that means a allowable number of packets that has to be sent from a sender to the receiver. That means how much packets that has to be sent, what is the range of this, that means what should be the n, that n we call it as window, that n we call it as window, that is the allowable number of sequence that has to be sent in the sender. As it moves out of as one packet acknowledgement is received, the another one will enter into the window. That is why we call go back n as sliding window protocol. We call go back n as sliding window protocol. We call go back n as sliding window protocol. Now, before we move, let us look at here. These are the sequence numbers. Let us suppose these are the sequence numbers that is being sent from a sender to the receiver. 0 packet is sent, packet 0 is sent and the acknowledgement is received for the packet 0. Packet 1 is sent and the acknowledgement for packet 1 is also received. Packet 2 is sent, acknowledgement is also received, but packet 3 while traveling the packet 3 is lost and the acknowledgement is not received and the timeout has occurred. What happens? The go back one will send the whole sequence again, the whole window. The window which we had defined, it will send the whole window again to the receiver. That means, if the timeout occurs at packet 3, it will send 0, 1, 2, 3 again. That means, it is going to send whole window to the receiver again. So, that is what they have explained in the diagram. From the sender, packet 0 is sent and the packet 0 is received by the receiver, and the acknowledgement 0 is also sent by the receiver, and then packet 1 is sent, packet 1 is received by the receiver, acknowledgement 1 is sent, packet 2 is sent, while packet 2, but while travelling it has been lost, packet 3 is sent, it is received by the receiver, and then since it has not received the sequence number 2, it has discarded the packet 3, and then it is going to send the acknowledgement 1 again. The previous acknowledgement is only it is sending, it is discarding the packet 3, it is not sending the acknowledgement for the packet 3. At packet as it is waiting, packet 2 timeout has occurred. When the packet 2 timeout has occurred, what it will do? When it will retransmit the whole sequence, it will retransmit the whole sequence to the receiver. That is what they have shown it in the diagram. Now, let us try to look at the FSM of a sender side of the go back N. As you could see in the diagram, it has only one state. The initial state has a transition, the initial dashed arrow has a transition where event is nothing, the action is, it is setting base is equal to 1 and next sequence number is equal to 1. When let us look at the upper action where RDT send, when it has to send the packet, what it will check? If it is checking if the next sequence number is less than base plus 1, because if it is greater than n, we should not send that packet, isn't it? That is why it is checking the condition. If next sequence number is less than base plus n, if it is less than that, it will make a packet, with the next sequence number, data and the checksum. It will make a packet of the next sequence number, data and the checksum, and it is going to send that packet, and then it is checking if base is equal to next sequence number. Only if base is equal to next sequence number, it is going to start a timer, and then it will increment the next sequence number. If it is base is not equal to next sequence number, it will refuse the data. Next, if the timeout occurs, what happens? It will again start the timer, and then it will start sending whole of a sequence to the receiver. That is what they have shown it over there. Next, when it receives the packet, and that packet is not corrupt, what it will do? It is going to get the acknowledgement number of the received packet. It is going to get the acknowledgement number of the received packet, and it is adding 1 to that. Here also it is checking if the base is equal to next sequence number. If it is equal, it will going to stop a timer, or else it will start the timer again. Now, let us try to look at the FSM of a receiver side of the go back N. As you could see in the diagram, the first action says when it receives the packet and that packet is not corrupt, and has a sequence number of a received packet and the expected sequence number. If the sequence number is the expected sequence number, that is also here checking it. If all the conditions are okay, then it is going to extract the data and it will deliver the data, and then it will make a packet of the acknowledgement, and then it will send the packet. After that, it is going to increment the expected sequence number. What is the initial action? It is setting expected sequence number to 1, and it is making a packet. Since expected sequence number is 1, we have to send the acknowledgement of the previous packet, isn't it? That is why it is going to make a packet of a 0 sequence number and sending the positive acknowledgement. So, with this go back when concept is finished. Now, let us look at the second method of the pipelining, that is selective repeat. The next method is selective repeat. What was the major drawback of the go back N? If one packet is lost in the sequence, it was sending the whole of a window to the receiver, isn't it? It is quite not necessary to send the whole of a sequence, as it has been some of the packets is correctly received by the receiver, and we have also acknowledged that, isn't it? That means, let us suppose if 0 is sent, if the packet 0 is sent and correctly received the acknowledgement, and the packet 1 is sent and the acknowledgement received, if the packet 2 is lost, what we will do? We will just select this packet, we will just select this packet, and we will retransmit only this packet. That is why the name selective repeat. Instead of sending the whole of a window, what we will do? Here we will going to send only the selected corrupted packet or lost packet instead of sending the whole window. In the diagram, we can see the sequence number of a sender side also, receiver side also. Instead of sending the whole of a sequence, we will keep track of each packet's acknowledgement. How are we going to keep track it? With the use of a buffer. Whatever the packets that has been sent by the sender, the receiver will buffer it, and it will check the sequence number, and then if it is not received, if it has not received the packet in order, what it does? It will buffer the next packets, and then if the packet 2 has been lost, what it does? It will send the packet, retransmit the packet again, and then as soon as the packet 2 is received, and then it will take the packet 3 and packet 4 and packet 5 remaining packets from the buffer. That is what they have shown it in the diagram also. Here packet 0 is sent from the center and it is received correctly by the receiver, and it is also delivered, and then that means it is not kept in the buffer, it is properly delivered, and then acknowledgement 0 is sent from the receiver, and then packet 1 is sent from the sender, and then packet 1 is also correctly received and it is delivered, it is not buffered, and then acknowledgement 1 is also sent. Packet 2, while transmitting, it has been lost, and then packet 3 is sent, while at the receiver check packet 3, even though it is received, since the packet 2 has not been received by the receiver, it will buffer the packet 3, and then it will send the acknowledgement 3, and then next what is happening? Acknowledgement 0 is received, packet 4 is sent, acknowledgement 1 is received, packet 5 is sent. Now let us look over there. The packet 2 timeout has occurred, that is why only packet 2 is sent from the sender to the receiver. After receiving the packet 2, what the receiver will do? It will deliver packet 2 and all those packets that were buffered. What were those? Packet 3, packet 4 and packet 5, all those things will get delivered. That means it is taken out from the buffer and it will get delivered to the upper layer. So, we are at the end of the reliable data transfer. At the end, they have tried to list out few mechanisms of the reliable data transfer. As you could see in the diagram, we use checksum mechanism. To what? To detect the errors if it is present, whatever the error that has been present in the packet, if the packet is corrupt, to detect that error we use checksum mechanism. Next is timer. Why do we use timer? To know, instead of keep on waiting for the acknowledgement, what we will do? We will put a timer. Within that time, if the acknowledgement is received, that no action is taken. If the timeout has occurred, what we will do? We will try to retransmit the packet. Next mechanism is sequence number. At the receiver, whatever the packets that the sender has sent, the receiver should know whether it is the retransmitted one, is it the new packet, is the packet that has the data that has been received, is it in order the sender has sent. To check all of those things, we use sequence number. Next, acknowledgement, that means a positive acknowledgement. If sender should know whether the receiver has received the packet correctly or not, isn't it? That is why we use acknowledgement. If we receive the positive acknowledgement from the receiver, what we think? The packet that the sender has sent, it is correctly received by the receiver. Next mechanism is what? Negative acknowledgement. If the packet is corrupted, if it is lost in the network, the receiver what it will send? It will send the negative acknowledgement. When the sender receives the negative acknowledgement, it will think that the packet is not correctly received by the receiver, we have to retransmit the packet. Let us look at the next mechanism is window or pipelining. In pipelining, what we do, instead of sending only one packet at a time, in pipelining we try to send a sequence or a multiple packets without waiting for the acknowledgement, and the maximum allowable packets that has to be sent from a sender to the receiver is called a window. So, with this, reliable data transfer, pipelined reliable data transfer protocol is finished. Thank you.